Thanks all for inviting me to speak this morning. As Taz mentioned, I joined Uber this year. I joined in January. All right. And I joined to lead battery development for the Elevate system. So what I wanted to do today was share with you guys our vision for urban air mobility and talk a little bit about some of the specific challenges we're going to face on developing that battery that's going to make that safe, convenient, and affordable transport. So something that we can all use in a lot of the world. All right. So at Uber, we think a lot about cities. We move people and things throughout cities. We're moving people, we're moving food, we're moving freight. We know that about half of the world's 7 billion people live in cities, in urban areas, and the projections are that more and more people are moving to cities. That's the way our culture and life is changing. When Raquel mentioned that, 20% of the population of Canada lives in Toronto, in a city, that's an example of how many people and how large a fraction of our population is in cities. Okay. So today, Uber operates in over 600 cities. We've got in 77 countries, we have over 65 million active monthly users. We move a lot of people. We move a lot of things all over the world. All right, so when we think about moving through cities, we realize that there's a limit of what we can do for urban mobility in just looking at the city as a two-dimensional plane. Okay, this is a rendering, an example. And, just like architects to deal with increasing density in cities moved up by making skyscrapers, we're also thinking, okay, where else do we go to deal with mobility? Well, we have to go into the third dimension. Now, you can do that with tunnels. You can do that with subways. People do subways a lot. If you go to Manhattan, there is an awesome subway network. If you go to most places in Asia, there's lots of trains, there's lots of subways. People have done that. It's super important for mobility in our cities, but it's not enough. We still have a lot of congestion. So if we want to move into the third dimension, we're looking at aircraft. Now, nice thing about the third dimension is the infrastructure requirements are pretty modest, okay? You don't have to, for example, put a tunnel all the way underneath the city, which might have a whole lot of infrastructure already underground. You don't have to try and punch another highway or another roadway through a super dense urban area where you're going to have to bulldoze buildings and move people and so forth. What you do is you build some very modest skyports and you let aircraft land on them. Okay, so from an infrastructure development perspective, this is actually fairly easy and a whole lot more palatable to city planners than you would think. So, okay. We looked at possible solutions, and there is one that exists today for urban air mobility. It's called helicopter service, right? Helicopters been around for a long time. A lot of cities have helipads. If you look around San Francisco, there's actually a lot of helipads. I was in Osaka last week. I got a chance to go up on top of one of the taller buildings, take a look around the city. There are a lot of helipads in Osaka and no helicopters flying there. And you kind of look at this and you go, huh, that's really strange. We have all this infrastructure already. Why aren't we using it? And, people want to ride in helicopters, right? Basically, we've done some promotional things where, Uber's offered helicopter rides and people sign up like you wouldn't believe. The team tells me that we did this in Poland and got 90,000 requests for rides. We were not able to serve all those customers, right? So people want to do this. But we've learned a lot about why helicopters are not really practical for ride sharing, right? Why all those helipads in San Francisco and Osaka and around the world just don't have helicopters flying there. The first thing is that helicopters are actually pretty slow. They are designed to hover, and they do that wonderfully. But in forward flight, they're super inefficient, and they're not really very fast. So the speed benefit of covering just a certain amount of ground miles is not really that high. So you're not getting a huge benefit in speed of transportation. And then the biggest thing is they're loud. And most of the heliports that are here have been shut down because the community does not want the noise, okay? So people don't want a helicopter landing on top of their building. They don't want the sound pollution. Then on top of that, you have high cost of fuel, high cost of maintenance, and you need really experienced pilots for good helicopter transport. All right, so to do urban air mobility, we need a different aircraft, okay? We need something that'll do vertical takeoff and landing because we're interested in cities, in a dense urban infrastructure where you don't have, we're not building airports, okay, with long runways. So you need the vertical takeoff and landing, but then you want the efficiency of a forward flying aircraft so that you can have high speed of that transport and just good energy efficiency. So you're looking at a vertical takeoff and landing, a VTOL. VTOLs have been made in the past. If anyone's an aerospace buff, they've probably seen pictures of military aircraft that do vertical takeoff and landings. I personally love the Harrier, but there's something called an Osprey, and you can see a variety of these things. These aircraft, however, have never made it into commercial use. And the reason is because they are really hard to transition from the vertical takeoff to the forward flight with traditional aircraft propulsion systems. Okay, when you want to take a jet engine or a propeller that's being driven by a combustion engine, and you want to take it and make it turn and then go forward, you get some really weird instabilities right in that transition, and it makes it really difficult to fly. Okay, so that's not going to work out so well with traditional jet engines, traditional propellers, or traditional combustion engine driven propellers. But if we go to electric propulsion, and if we can distribute that electric propulsion along lots of different rotors, we can eliminate that problem. So now transition can be handled much more gracefully. You're not taking your main drive rotors, for example, and having them to do multiple jobs. So this is a reference model, and let me see if I can play it again. Just to show you what one of these aircraft, and this is a concept, but you can see that you've got rotors that are helping lift the aircraft off the ground, doing that vertical thing that then recess back into the aircraft, and then you have forward flight propellers. So you get all the benefits of vertical takeoff and landing, you get the forward flight, and you get a graceful transition. Now, there's one other nice thing about distributed electric, well, there's a few nice things about distributed electric propulsion. First off, there's a lot of rotors on there, there's a lot of propellers. So the potential for enhanced safety is really high. You don't have a single point of failure on the aircraft that will make it land abruptly. So you have a lot of safety features, and those propellers are small. So the resulting sound that you hear from one of these aircraft is considerably less than you would have for a helicopter. So Uber studied the whether eVTOL could be used for urban air mobility, whether this would be cost effective, convenient, and so forth. And this is an example of a route that some of the folks in the room probably are pretty familiar with. If you want to go from downtown San Francisco, like in the marina, to downtown San Jose, depending on the time of day you go, this could be a two-hour trip, right? On UberX, it'll take you about an hour, 40 minutes. If you're taking Caltrain, you could be over 2 hours, okay? With the aircraft that we're considering, this trip time would be down to 15 minutes, which is pretty compelling, and that makes a difference to people, right? Now, you go, okay, 15 minutes, what's it worth to me? We think with these aircraft, we think in our technology development path, we can get the price of that down to something that's comparable to an UberXL ride on the ground per person, right? So suddenly that's a price that you can afford to get across town that fast. Yeah. All right, what would this trip look like? Let's see if we play. All right. Our intention, yeah, I guess there's no sound. That's all right. Our intention is to have this to be a push a button, get a ride. Okay. It just becomes one more available option when you open Uber. And then Uber coordinates the entire trip. So they get you to the skyport, and then you take off, and you'll land another skyport, and then another Uber car will take you to your final destination. We are not planning to take off and land in the people's driveways. Okay, the question about like, oh my God, you're going to have like a snowblower sitting outside your house when your neighbor lands in their air taxi. No, that is not our vision. Okay, this is from designated skyport to designated skyport, and the intention is to locate the skyports in areas that are high traffic, but also to make sure that the noise that we add from the Elevate operations is going to blend into the soundscape around the skyport. Okay. Trips are going to be pooled. This is an on-demand versus scheduled service. You basically get a bunch of people together like Uber Pool, and that's what makes it economical. All right. We're going to charge during loading and unloading, and then in lull times in between when we have passengers. So these are short flights, and we're going to have pilots initially, and hopefully then move to autonomy, because for the scale we want to go to, there aren't enough pilots in the world. Okay. All right. Let's see. So how do we get there? We have a roadmap. It's aggressive. We want to start demonstration flights in 2020. That's going to be in a few cities. And then 2023, we want to begin commercial operations. Depending on your culture, that's either no time at all or lots of time. But it is, from a practical perspective, it's an aggressive schedule. In 2025, we're looking at hundreds of aircraft per city in quite a number of cities, and then fully scaled operations in 2030 to 2035. So this is not tomorrow. This is a long-term vision for Uber and a long-term plan. How do we get there? We're not building aircraft at Uber. We are building an ecosystem, okay? Where companies have experience building the parts of this ecosystem that we need, we're inviting them to be partners. So for example, we've announced a number of aircraft design and manufacturing partners. Some of you guys know the names of uberAIR, Bell Helicopter, and so forth. These folks know how to make aircraft, and we expect them to make a whole variety of aircraft for our system, and we expect them to evolve these aircraft over time, so that this is not just we're going to make one thing. This is like, we're going to make aircraft that do this, and then we're going to keep making aircraft that do this and keep improving them. We've also announced some infrastructure partners. So, for example, ChargePoint makes charging hardware. You can charge yourself or your EV with ChargePoint's hardware around San Francisco. They've agreed to be our partner in developing the charging infrastructure for these aircraft. And then we have real estate partners as well, folks that want to build the skyports for this. Okay. Where we don't find partners, we're developing internal teams to fill the ecosystem gaps. So these are some of my colleagues. Mark Moore came out of 30 years at NASA. He basically developed distributed electric propulsion at NASA, championed it, pushed it, and is really considered the father of that whole area. Tom Prevost is our director of aerospace systems. If we're going to have a lot of these aircraft flying at relatively low altitude, you can pretty much figure that the current air traffic control system is not going to do it. So we have to develop one entirely for these vehicles and for these systems. And Tom Prevost is going to lead that. He did similar work at NASA for unmanned vehicles. Stan Swiatek is our head of operations. He comes out of, he was a helicopter pilot in Special Forces. And he's thinking a lot about, where do we find pilots? How do we train pilots? What do our skyports need to look like? How do we have to operate them? Dave Josephson's an acoustic and sound systems expert. He is studying what it takes to make one of these eVTOL aircraft blend into the soundscape of the surrounding city. It's not just about how loud an aircraft is. I think all of us know that. Sound is not just about volume, it's also about how it's perceived by you. What sound is annoying, what sound blends in, what sound do you not notice? So he's an expert on that, and he's been working at looking at that. And I joined Uber to develop a battery. Okay. This is pretty challenging. We want to be electric, all electric on these aircraft. Some people are talking about hybrids. We don't want to add hydrocarbons into the next transportation solution for cities. We want this to be green. We want this to be carbon neutral. We want to be all electric. So that makes for a very challenging battery development. So these are some of the requirements that we've put together for what the battery has to be. And I'll walk you through a few of them and explain some of the implications for this. There's a lot in here, so we'll cover a few of these things. Okay. So the first thing is the range. Range is actually kind of modest. We only want to go 20 to 60 miles with these aircraft. Okay, that's completely different, by the way, from what aircraft designers have typically made aircraft for. But it's a modest range that covers most cities. So the battery pack, capacity-wise, doesn't actually have to be that big. It's 150 kilowatt hours. To kind of give you guys a reference point, Model S, right, you can get a 100 kilowatt hour battery pack for right now, do about 300 miles. Okay, now that's on the ground. That vertical takeoff and landing draws a lot of energy, right? But if you look at that and you go, well, heck, you know, our electric cars are pretty close to this. We should be able to get there. Okay. The other thing that you need to look at is, though, that these are very heavy duty cycles. Where you take, in most people's personal electric car, it's just like everyone else's electric car. It's parked 95% of the time, right? When you design a battery for a personal car, you design it for the way people use that car. This is a different use case. What we're looking at is, you know, loading passengers on this thing while this aircraft is charging. You do a very high power vertical takeoff. You do 15 minutes of flight. You land the thing, and it's another high power draw. Then you unload people. You load more people. You're charging in between that, and you're going to do this constantly. Okay. We estimate that, you know, one of these aircraft is going to put like the equivalent of 200,000 ground miles on it every year, right? I mean, who's driven a car out to 200,000 miles? Like, has anyone rolled 100,000 miles? Who's rolled 100,000 miles? Yeah, it takes a while, right? Yeah, these vehicles are going to be really, really doing a lot of work, and so that battery is going to be different because of that. All right, so the really tough thing is the energy density. That's a 400 watt hour per kilogram cell. Best cells right now that Tesla uses are somewhere in the 220 to 250 kilowatt hours per kilogram. Now, this is for commercial operation. This is 5 years away. There are a lot of technologies on people's roadmaps, on battery makers' roadmaps, that suggest to me that we're going to actually be able to get there. You know, things actually in the battery industry, they change faster than you think. It doesn't seem like it, but you know, they actually do. Who had one of the flip phones before we had smartphones? Yeah, I'm old. Yeah, okay. It wasn't that long ago, right? Same time, like getting to 400 watt hours per kilogram is really only a beginning. That's like one big hurdle, and that's a cell chemistry hurdle. But beyond that, when we start building a battery pack to actually handle cells that have that kind of an energy density, we have a lot of safety considerations to think about, and we have a lot of development to do to make those battery packs safe. One of the big things that I worry about is, okay, if you've got cells in a battery pack, eventually one of those cells is going to have a bad day, and you're going to have a thermal runaway reaction. It's kind of, if you have enough cells, you have these things occur. So you can try to say, oh, that's never going to happen, but I've been around long enough, I know it's going to happen. So what you say is, okay, I'm going to assume that I'm going to have a cell that's going to go into thermal runaway in my battery pack. The hard truth, we're going to face it, and we're going to then mitigate it, and we're going to deal with it. So what you do is you develop your battery pack to have propagation resistance. The intent here is, okay, you have a cell go into thermal runaway, and no one should care as a result, okay? If you design this battery pack properly, if a cell goes into thermal runaway, maybe you see a puff of smoke somewhere and nothing else bad happens. That's a really hard design challenge, by the way. There's a lot of pieces of all the heat transfer that you could ever imagine, plus combustion, and a whole lot of material development takes to do that. Okay, but that's one of the big implications of these higher energy density cells, that we have to develop that safety architecture as well. Then on top of it, you say, okay, I've got this very energy dense battery pack, and I'm flying it through the air in my cities, and I'm landing it on top of buildings in my cities. If I have something bad happen, for example, someone decides that they don't like us and they decide to catch, do arson and, catch one of our aircraft on fire, or something else happens, you have a fire at the skyport. How big is the fire going to be if it hits the airplane? Like, you have to think about this. You can't leave this big energy storage system out there and then, expect that your municipal fire crew is going to come out and put the fire out and not even think about what that's going to look like to them, right? So you have to limit the heat release that your entire aircraft is going to be providing, which is, it's a very scary scenario, but we're engineers. We don't just think about the optimum scenario. We also think about what happens if things don't go optimally, right? So we have to prepare for that. And that gets tricky. With these higher energy density cells, people wonder about, well, how big's the fire going to be? Are we going to have explosions? No, we're not going to have that. Okay, and we're going to limit the size of the fire so that basically if a fire crew shows up, they can put water on this thing, they can not put water on this thing. It's going to be not a big deal. It's not going to be any different than if they respond to any other fire. That's also a super hard design challenge, but I think it's one we can achieve. Okay. All right. The fast charging. People who don't know batteries maybe don't know what a C-rate is. It's a way you talk about how fast you have to charge the battery. So you have to be able to get the full capacity in. 1 C-rate means within 1 hour. You got to get the full capacity in. We're looking for being able to push the full capacity of the battery into the battery in about 15 minutes. That's what a 4 C-rate means. That's really hard. Right now, fast charging Model S, 45 minutes to get 100 kilowatt hours of capacity into a Model S pack. Okay, we're looking to drop that time by a lot. That makes some very hard cell design. It also means that your battery packs have to be able to handle those kind of high current loads. That has implications for things like fuses and current collectors, and even just the high voltage lines in your battery. Then you have to have a DC fast charger that's actually able to deliver that kind of power to your battery pack. ChargePoint tells me they've got that covered. I'm like, yes, one thing I don't have to do is awesome, right? But then you also have to have an electric grid that's going to support multiple fast charging aircraft on the top of buildings. And that's actually a huge challenge for cities. It's something that they're going to face with electric vehicles too, because as you start electrifying transportation, you use a lot of power in cities, and you think you're going to have a whole lot of cars charging, and then you're going to have a whole bunch of these aircraft charging, and then you've also got all your electric trains and so forth. You have to have a grid that's really delivering power to the city. That's going to be a challenge for the future. So one of the other things that we're dealing with is cycle life is not necessarily going to be awesome on these batteries to start with. We're going to be pushing the technology really hard, and we're going to be pushing for really a lot of fast charging that tends to degrade batteries. So we do expect that we're going to be changing batteries out of these vehicles fairly often. And of course, if we're going to do the type of throughput that we really want to do, even with great chemistry that's very optimized, we're still going to be changing these battery packs very often. So, we're working with the aircraft manufacturers because, typically they don't change the jet engines off a jet that often. They don't pull the piston engine out of a small aircraft very often. That's like a major, right? But here we're talking about removing the power source and replacing it annually, right? And then the other thing is some of this stuff's going to have to happen right on our skyport, right on the pad in the skyport. It's going to have to be fast, and we're going to have to move, batteries and aircraft to do that. So that's another nice mechanical engineering, electrical engineering challenge. So that's going to be fun. But it also means that we're going to be building a lot of batteries. So we're trying to aggregate basically component demand and simplify maintenance and make sure that the battery pack, how it integrates with the aircraft, is something that's amenable to us being able to change it often. The good news about this is that as we evolve our battery technology, we should be able to basically replace an older battery that may not have great performance with a new one and be upgrading the aircraft throughout its lifetime with range and performance, which is really kind of cool and not what you typically expect. You usually expect that your existing hardware is just kind of going to become not so awesome and not so awesome and not so awesome. And here, okay, the aircraft is one thing, the battery is just going to keep getting better. All right, and then finally, one of the big challenges is redundancy and reliability. Uh-oh. All right, cool. All right. So right now, we have to achieve for aircraft, we have to achieve new levels of redundancy and reliability. It's one thing to have your electric car kind of lose power and you push it off to the side of the road and you wait for a tow and it sucks and it screws up your day. But, it's a whole nother thing to lose power as you're trying to do a vertical landing in an aircraft. That makes for a really bad day, right? So, we can't allow really bad days to happen. And that's something that goes beyond even where the industry is for automotive, right? So we can't lose power. We always have to be able to land the aircraft. We have to have super accurate fuel gauging because if we don't, what's going to happen is we're going to have to carry much more reserve capacity on the battery. FAA is going to demand that we have some kind of reserve capacity for our missions. And the less accurate our fuel gauging is, the less confident we are that we know how much capacity and power we can deliver, the bigger that is going to be and the less efficient our aircraft are going to be and the more expensive. So we have to get that right as well. And then, the way you really do this is you really have to actually look at data from the battery. You can't just have one little light that tells you, I'm good to go or I'm not good to go. This is much more complex. You have to actually really understand your battery. And that means quite a bit of data transfer from the aircraft, from the battery to an internal server, and a lot of smarts about looking at what the fleet's actually doing and making judgments about fitness to fly from the fleet. And that's something that we're going to have to do for the battery. It's going to be something we're going to have to do for a lot of the systems on the aircraft as well. That's going to give us better safety than the helicopters of today, right? We're aiming to be basically twice as safe as your personal car. And that's a tall order for small aircraft aviation. But I think we can get there too. So, that's some of what we're up to. There's a lot of us working on this. It's an ecosystem. It's not just a thing. It's not just one product. It's an ecosystem. This is a very collaborative effort. It has to be, because you don't make an ecosystem all on your own. So we're working with a lot of partners, a lot of different people, a lot of different technologies. And we look forward to working with y'all because, it's closer than you think.